Thanks, Alex. Stage is yours.
All right, thanks. Welcome again to the class. So today we're going to continue this journey through Spintronics. And just to remind you a little bit about the previous lecture, so we gave some motivation why Spintronics could be useful. So it could be an alternative or a complement to the current electronics, because using spins instead of charge or spin in charge could bring some advantages. We discussed a little bit about this. And so we saw that in order to, to make any application of Spintronics, we need to make this spin relevant. So if all the states are spin degenerate, so I cannot distinguish between a spin up and spin down, although they have the same energy, so we cannot really do any application of that. So we need to make the spin relevant. And there are two ways. So the way of making a spin relevant is to break the spin degeneracy. There are a couple of ways of doing that, but one of the ways is to break time reversal symmetry. So this, like in this specific case of exchange interaction, so you get this band splitting. So essentially, if there is no exchange interaction, so is this J change is zero, you will have a dispersion that looks like that. So two parabolas. These two parabolas that we have here, just one on the top of the other. So it will be doubly degenerate. So at this point, you have two spin states, up and down. So if you, at any value of k or any value of energy, you have the same amount of spin up and spin down. So now when you put this exchange splitting, so you see this other term that is proportional to n times sigma, what happens is you just split these two bands. One of the bands is shifted up. This will be the purple band there, and the other one is shifted down. So for a spin up, it's shifted down, and for a spin down, it's shifted up. So you end up with these two. So one, and the other is shifted up. Okay, and this energy difference is just the exchange energy. Okay, so that's the idea. But now you see, because the bands are shifted, so you see that there are more states in the spin up band, so the red one. So you can put more electrons in there than in the other one. Okay, so it means you will have more electrons with a spin up than a spin down. And in this bucket figure that we have here, essentially, we can, have this like a couple of buckets. One have more spin up electrons than the other. So this creates this spin imbalance or this spin polarization, and then we can eventually use the spin to do something. Okay. Now this is very nice for ferromagnets or magnetic materials because this is already in there, but it is a challenge to use semiconductors. So we know that semiconductors are very good for electronics because you can make it very clean, very nice, but most of them are non-magnetic. So how to then create this spin polarization in the semiconductors? But there are different ways of doing that. And one can do a spin injection, a spin extraction, electrical or optical pumping. So you can also pump spins with circularly polarized light, so that you give orbital momentum and then it transforms into spin. So we can also have magnetic proximity effect, magnetic field, or a spin filter. Magnetic field is typically not as good because the J factor is small, so you will need a very large magnetic field typically for that. So let's have a look at one can do something that is called spin filtering. And it's very, it's very similar to what happens to light when it goes through a polarizer. So let's say we have this situation here in which I have two normal materials. So by normal it means they are not magnetic, so they are unpolarized, spin unpolarized. And so in this one we have, so we pass a current through this material, through this structure. We have three layers. And in this normal region, I have the same amount of spin up and spin down, so there is no polarization. There is no preferential direction for a spin. Now, when they go through the ferromagnet, so in the ferromagnet you have more states for a spin up that are available for this electron to go through than electrons with a spin down. So you have this current will be spin polarized, and then more electrons more electron with a spin up will go into the other side than with the spin down. So essentially you are injecting, or in a way, these spins from the ferromagnet into this normal region. Okay? So this is a non-equilibrium spin polarization. You need to pass the current. If there is no current, so you cannot inject the spins. Okay? So I put this example here for this, with the 3 layers to make this analogy with the polarization of light. So it's the same. You have unpolarized light. You have a polarizer. After that, the light is polarized. So here is the same. You have a current here at the beginning, which is unpolarized. The ferromagnet acts like the polarizer. After that, the current is polarized, spin polarized. So on. Okay. But you can do this just with 2 layers, actually. So this will be, and you can have a spin injection into this normal region or a spin extraction in dependence on in which direction you are passing the current or in which direction are the electrons flowing. So in this first case here, so the current is going in this direction, so the electrons are going from left to right. And because we have more electrons in these bands with the spin up, so we will have more electrons with the spin up going into the normal region. So we will have more electron with spin up, so creating polarization in this normal region. This polarization will penetrate to somewhere, but then of course in the normal region you may have scattering and so on. We have other mechanisms for spin flipping, relaxation and so on. So it may not go through all the material. Now if I reverse the direction of the current, then what happened now is the electrons from the normal region are going to the ferromagnet. So in this ferromagnet, in this magnetic region, we have more states available with the spin up. So there are more states with the spin up that are able to go from the normal region into the ferromagnet. So you are losing spin up electrons, so you end up with spin down electrons. So you get the spin down polarization here in the normal region. So this is called spin extraction. So I'm just extracting the spin up from the normal region. In the other case, I was injecting the spin up from the normal region. All right? So again, this is again a spin polarization that is generated in a non-equilibrium situation. You need to pass the current. No current, no spin injection, no spin extraction. Now you can also inject the spins by other means in an equilibrium state, and this is done via the magnetic proximity effect. So this is more or less a picture here. So let's say that you have a magnetic layer here and a normal layer on the other side. So there are states from the magnetic layer that can penetrate this non-magnetic layer. So essentially, some states that are spin polarized from the magnetic layer can penetrate in the normal layer. Now, this penetration length is typically very small. So if the normal layer is very, it's very thick, then this effect is going to be very small. So because most of whatever you measure in this normal layer will be dominated by states that are not really feeling. All these states here that are, let's say, localized here, they are not feeling at all this ferromagnetic layer. So whatever you measure in this layer will have very weak influence of this proximity effect. However, if you make the layer smaller, thinner, then it starts to become important, the proximity effect. That's it. That's why you typically use very thin layers or two-dimensional materials to increase this magnetic proximity effect. So this can happen at equilibrium. So there are no currents here. It's just an equilibrium situation. You can also break a spin degeneracy via spin orbit coupling. We will talk actually about this later on. And you can also use induced proximity spin overclocking through proximity effect. And the idea is the same. So you have a layer, and the wave function in this layer can penetrate into the other wave function, into the other system, and then generate or induce spin orbit coupling. In this specific case, I'm giving a couple of examples here of iron. So this is I have a layer of iron here. In this first case, I have 8 monolayers of iron, and on the top of gallium arsenide. So at the interface of iron and gallium arsenide, you are breaking the inversion symmetry. And then there is a spin orbit coupling generated there, so I will talk more in detail about that. But then, independence of how these states from iron penetrate into this barrier of gallium arsenide, if it penetrates a lot, it will pick more information about this change or break of symmetry at the interface, and we have a stronger spin orbit coupling effect. If, and now, so you want this penetration to be large, actually, you will need to do this ferromagnetic layer very thin, so that the states can penetrate more into the gallium arsenide. Okay. Now, here are experiments, actually. These experiments are measuring the so-called crystalline magnetic, anisotropic magnetoresistance. I'm not going into detail, but what I want you to see in this is the change of the symmetry. So iron is, have a 4-fold symmetry, and gallium arsenide. So the interface of iron and gallium arsenide have a 2-fold symmetry because of the structure of the atoms and so on. Now you have 8 monolayers, like in this case, when you make the measurement, you see something that has like a 4-fold symmetry. You see 1, 2, 3, 4. So you rotate by 90 degrees, you get the same thing. So it means that in this case, the effect of this interfacial gallium arsenide is very small. So this penetration is very small. There is almost no spin orbit coupling proximity. But if you make this iron layer thinner, so now you decrease the thickness from 8 to 4 monolayers, then the states in iron start to penetrate this gallium arsenide barrier and pick up the information, this lowering of the symmetry due to the interface. And you see that what they measure go from 4-fold into 2-fold symmetry. So this is a very nice experimental demonstration of this proximity effect. All right, so now we know how to inject a spin. We can have a spin also in semiconductors. We need to characterize the spin. So we need to find some equation for the spin density, for the spin current. In the same way we have charge currents, we will have spin currents. So to define the charge current, typically what one do is just to calculate the continuity equation for the charge. So what is the continuity equation for the charge? So if I have a charge density, and I calculate the rate in which this charge density changes, it should be equal to what? It's conservation of charge. How it is related to the current density. Right. Thanks. All right, that is the continuity equation for the charge. Okay. And this is just a manifestation of the conservation of the charge. Now, a spin is not conserved because charge, well, I have the charge of the electron, I cannot change this charge, it's always the same charge. Okay. But the spin I can change it because if up, I can flip it, it can go up, down, so spin is not conserved. It means I would have something similar to that, but I won't have zero here because its spin is not conserved. Okay? So I will have something here we will see, which is we call a spin torque. It's a source that for the spins. Okay. All right. So I will go to the node to work a little bit, show you a little bit how to get this, but it's very simple. It's the same procedure you use for, you start with the Schrödinger equation, and you want to go to this equation to find the definition for the current, for the electric current. or the probability current. The same you do to get this, we will do it for the Hamiltonian that we have. So it's just very simple. We will go into these details right now. Okay. Let me switch to the notes. Or maybe it's, I think I have it open there. Yeah, it's probably better. Okay. So the continued equation. So we start. By the way, this is also a nice way to define, because you may not know how to define currents for something, but if you do that, so you will get this definition of the current from the equation itself. Okay. So what we start with the spin density. So the spin density is just the expectation value of the spin, right? So this wave function depends on position, so this S, large S, also depends on position. And I have three components, X, Y, and Z, which I am, summarizing with this J in the subindex. J's, those are X, Y, and Z for the three components. Now, if we calculate the derivative with respect to time, well, we'll get this expression here, right? Now, what we have here, derivative of the wave function, and this derivative with respect to time of the wave function, we can get it from the time-dependent Schrödinger equation. So the time-dependent Schrödinger equation will be this equation here, and I'm dividing the kinetic part plus everything that is not kinetic, okay? So, H kinetic is just the kinetic energy, and delta H is whatever you can have in this Hamiltonian, whatever interaction that is not kinetic energy. So you can then, from this equation, easily get what are the derivative with respect to time of the wave functions, and the derivative of the complex conjugate or Hermitian conjugate of the wave function. And then you can substitute these two expressions in this equation. It's just simple algebra. And you get into this equation here. So the kinetic part is essentially given by the Laplacian. So you get this equation here in terms of the Laplacian. So you see this actually, if you look at the definition for the, you look at this equation, the continued equation in the case of the, of just charge, it's very similar. So, you put sigma here, this tends to 0, and then you put sigma here like the unit matrix, then S will be just the charge density, right? So, see, if I put sigma here like the identity matrix, and apart from this factor of h bar over 2, I will get just the charge density or the probability density. So you get an equation that is very similar. The only difference is this extra term that we get here. So this term, you can rewrite it like a divergence by using this mathematical identity here, and then you can get your rate equation for the spin density. And you can write it like this. It's a minus the divergence of this term plus this other term. And so then one can identify this term inside the divergence like the spin current. Okay. What is the other term? Well, the other term is what we call spin torque. So we can then write the continued equation, which is similar to this, but now we don't have 0, so we have spin torque here. We could have this spin torque 0 if the spin is conserved. Then yes, then it will be 0 here because tau will be 0. But in general, it's not so. In general, we have spin torque in there. Now, what is the problem? This is very nice, but there is an issue with this, and the issue is that actually, well, it's not uniquely defined the way I put here. So somehow by hand I put this spin current into this divergence, right? So in principle, I could decompose this spin torque into some divergence by something else and then sum up something. So I will change then the definition of spin current and the definition of a spin torque. Okay. So I remember 20 years ago there was a big, this was a big story. So people were trying to define another spin current as a way to be conserved and so on. And it took like 5 or 6 years and people realized that actually it doesn't matter how you define it. You have to be consistent to what you call spin current and what you call spin torque, and of course how it is related to what you measure. Okay, so we have then the spin current. I particularly like this expression. Actually, you may define it in a different way, but this is very appealing because this looks like what you will expect for a spin current. So for charge current is charge time velocity. Well, here our charge time momentum divided by mass, which is the velocity. Well, this is the definition that you get from this expression. So you see sigma with the derivative with respect to s, which is essentially the momentum. So it's like spin times velocity instead of charge times velocity. Now the spin torque comes from these other terms, and it depends on whether you have the Pauli matrices commute or not with any other thing that you have in this Hamiltonian. If you have, for example, a magnetic field, well, it may not commute because the magnetic field we have sigma dot b in the sigma interaction, and then sigma, the Pauli matrices in general don't commute with each other, so you may have a spin torque. So here is what I mentioned, just more explicitly written here, that you could define this current in a different way. So let's say that I could define the torque in this way here. So I don't know if you see my. Okay. All right. So I have this spin torque here, and I can define the spin torque like some quantity minus some divergence of another quantity. All right. And then I can put this term here into the divergence, and then say, okay, my spin current is not J, it's J plus J tau, the new one. But this will also change accordingly the spin torque. So I could do that, and I would have different ways of defining the spin current and spin torque. But the important thing that they are related, as long as you are consistently defining them, you should be okay. It took a while for people to understand that. But so I think now we understand that this is okay. Now you can rewrite the spin, you can use this expression here, and try to rewrite this as an expectation value and show that the spin current operator is actually given by this expression here. So 1/2 and the anti-commutator of velocity and spin, which is very appealing because, well, for the case of the charge, it will be the same. But you will have, instead of velocity spin, you will have velocity and charge. So in the case that there is no torque, so the spin is conserved and the spin torque is 0, then so one can find actually that the spin current is actually the difference between the charge current for spin down electrons and spin up electrons. So essentially this relation here. So we'll skip, the demonstration is done here, all this. I just will skip it, but you can have a look at the notes. It's done step by step in there. And you can see that this is what you will get. So it's essentially this part here is the charge current due to electron with the spin up. This is charge current due to electron with spin down. So you get the spin current, if the spin is conserved, it's just the difference between this charge current for spin up, spin down. And of course the charge current, the total charge current is the sum, but the spin current is the difference. Now this brings you into a very interesting situation in which the charge current could be 0, but the spin current not. Okay. So you can see that in the case in which the charge current of a spin up and a spin down are opposite, so the total charge current will go to 0, right? But then the spin charge current, the spin current is not going to be 0. So in that case, we will have a pure spin current. So we won't have combination of spin current and charge current, but only spin currents. And this will happen, of course, if this charge currents of both of spin up and spin down are different from zero. Otherwise, all the currents are zero. All right. So, any question? Yes.
Can you describe again why the charge current is zero while the spin current can be not zero?
Right. So, if the spin is conserved, okay, so we have that the spin current is the electric or the charge current of a spin down minus the charge current of a spin down up minus the charge current of spin down. And the charge current is the sum of these two, right?
Yes.
So let's say that the charge current is zero. So you get here, then the charge current is minus. All right? When you put this in here, and you will get is twice. Okay? This is different from zero. If these currents are different from zero, of course. If you have this, yeah, then all the currents are zero. But you may have a situation in which these two are not zero, but opposite, and then you
Which
get.
is spin up electrons go to this side and spin down electrons go to this side. That would be the situation always.
Right.
Okay.
So, yeah, so it will be spin up and spin down this. So, electrically, there is no current. So, the same amount of electrons are going that way than in that way.
Yeah.
But for the spin, because it's the difference, so. Okay. All right. So
Alex, I have a question. If I will take these gauge formulations which you showed us yesterday with this Iliad paper, and if I will make like a minimal coupling and then make a derivation, like standard with current can be derived via minimal coupling and then the
So you will get a definition like this. And the difference is that the velocity, so the momentum, you will have this covariant derivative, right? So which
okay, so it will give this.
covariant derivative like this. Yeah.
For this definition of spin current, can we distinguish that it is, if we get the number or we distinguish that we have spin up and spin down for along the same direction. Spin up is double, the magnitude of spin up is double spin down. And another case is spin up, spin down, and the same amount of the flow along opposite direction. For example, the first case.
All is here, okay?
Yeah, but I think they will get the same value. Spin up is twice of the spin down, flow along the same direction. So
Right.
we will get some positive number.
So if this is twice if this up is twice this, you will get one spin down. So it's everything, you can just use it here. Any case. Okay, so let's say that what you're saying. Okay, let's say that the current for a spin up is twice the current for a spin down.
Yes, exactly. And the same direction, like flow along the same direction.
Okay.
Yeah. And then the second case is.
So if you put this in here, you will get just 2 down minus down is 1 down. 1 charge current down. So this, just substitute this in this equation for the spin current.
Yeah.
So you get 2 times.
So you mean the spin current is spin down? You mean
The resulting will be spin down, yes, because Well, you are telling that the spin up is equal to time spin down. So everything will be spin down.
What is confusing you?
I thought because the spin up current is larger than spin down, so it should be spin up.
No, like you
But then
just
that is
said
twice.
you're having spin current, and you are having twice large spin current here. So effectively, the total. So you are transporting two together. There is no spin current, right? So only one is transported. So it's effectively the total.
Then spin up, magnitude of spin up is twice of spin down.
Yeah, that's exactly what is written.
So the result should be spin up. Because spin up is larger than spin up. Spin up, the magnitude of spin up is twice than spin down.
It depends on so in the direction they are moving, right? So
And
They-
the same direction.
if they are moving in the so if, because you have the minus here, okay? So you need let's see.
Oh, okay.
So let's say that you have, just make it, let's say that you have two electrons with a spin up, okay? And they are moving in this direction.
Yeah.
So this will call it, I don't know, J up. Okay. And then you have, one in the other direction. In which direction is the other one?
One spin down along the same direction.
One will spin down here
Yes.
along the same direction.
Yes.
Okay. So then the result will be, should right.
Yeah. Right.
So,
And then
Which is exactly fine because one spin up is the same as a one
so
spin down.
this is just, you just canceling this current.
Yeah.
So you are just transporting this one.
Yeah, I don't know why your result is the best. I mean,
Well, but I saw this situation is different from here because okay. No, what is the problem? So this is just the same.
I think you are calculating the magnitude for the equation. So which means the magnitude of the total spin current is one spin down plus this represents the spin up current. Or for JS, you just calculate the magnitude of the spin current.
Yes, the magnitude, yes.
Yes, so which means this spin current is in magnitude of the spin down current, but not meaning that this is the spin down current.
That is correct.
so we can know the magnitude. Just which
Well, you should know what is, so you know the directions of all the currents. You should know what is the, so the thing is, let's say that this is moving from left to right. This is also moving from left to right. So you should get,
I think you need to compute like the density, spin density, and then you will see that it's current, but you will see what is the density which it carries. So current is just telling you the direction, and spin density you would need to calculate like the difference outline from. I think so.
okay, so I will figure out that for the next lecture I will give you an example. I need a little bit more to give. I just try to remember that. So just to continue because I have
Alex, we
this.
still be the jet lag from this 4 a.m. But next week we can also
No, okay, so we'll figure out. then we have the continuity equation, we have the current. So one problem with the spin current is that it's very difficult to measure this. So if you say, okay, charge current, I can measure it easy, but the spin current, how to measure this spin current? It's not an easy task. Most of the time what you do is actually to convert these spin currents into some electric signal so that you can measure the electric signal. This is what in practice is most of the time is done. And there are different ways you can do that, so I'm not going to talk about this in the course, but there are different ways of converting spin currents into electric signals. And then you can measure electric signals. All right, so let me go back to the slides. So as an example here, I have the case of we analyzed before. We have this case with the chain splitting. With the Hamiltonian of this model is just given by this expression here, and you can calculate you can use this to calculate the spin torque, which is essentially given by the commutator of this term here with the spin matrices, Pauli matrices. So it's essentially given by this expression. So you get that the torque is just the cross product between the direction of this exchange field and the spin. Okay, so this actually can be used in practice to generate spin weights. So you may have, let's say, two different layers, and in these two, let's say you have a layer with a magnetization that is in a given direction. You have another layer that have magnetization slightly different, and when electrons are, you pass a current, electrons that are coming from this layer, so they are polarized in this direction, enters into the other material, have a different magnetic direction, and then you have this torque which push the magnetic the magnetization a little bit out of this axis, and eventually it can precess around this axis. So it can also propagate along different directions. You can have generation of spin waves. You can also use it for switch magnetization. So you can pass current that is polarizing a given direction, and then that is not the direction of the magnet that you have. Then through this torque, make a rotation of this magnet and switch magnetization in the other material. Okay. All right. So, any further question before going to the next topic? Are we good? All right, so let me go to the next topic then. And so in this second topic, so we have one of the ways that we show that we could break the spin degeneracy was to use exchange fields. And in this lecture, I will show you that actually, even with a magnetic field, you may find a way to break the spin degeneracy, and this is through spin-orbit coupling. So I will try to show you. It is really very, there is a lot of calculation. This is relatively simple, but many things are long. So I just will show you more or less how it's done, but without going through all the details. So I will post the notes with more details, but I will try to give the ideas and then, go from some math expression to the other, but without all the intermediate steps, okay? So we have this equation. Actually, we had, discussed this Pauli-Schrödinger equation in the previous lecture. And we saw that, here we have the sigma splitting, which depends on the G factor. G factor for the electron is roughly 2. And so this is the Bohr magneton, which is very small. So, this splitting is usually very small. You will need to put a really very high magnetic field to get anything observable from there or in materials. So you have an atom where you can measure the splitting. But if you want to use it for any device, so this has to be large, and you cannot get it large. Okay. So this lambda knot here also that is coming for the spin-orbit coupling for the electrons in free space is also very small. It's proportional. It's actually equal to h bar squared over 4 times c squared. So there is a factor of 1 over c squared. C is a large value, so this is very small. So It means that for electrons that we have, in free space, there is no use for doing spintronic with this electron. So the story now that when we have a material, well, these electrons are not electrons anymore, so we call it quasi-electrons, because they are interacting with all the other things that you have, all the other atoms and so on that you have in the materials. And we will show that for the case of semiconductor, actually you get a similar equation like that one, but with all these values for the mass, the G, and the lambda renormalized with material properties. So that is the thing that, can bring these values up when you're renormalizing with the material properties, and then so they become much larger. So for the case of lambda node, I think it's like 5 orders of magnitude larger than the one that you have for the electrons in vacuum. So I will, this the outline of the talk. So from atomic spectra to electronic bands, then a K.P approximation, which is used to describe these bands of semiconductors, downfolding technique to get an effective Hamiltonian for the conduction electrons. And then, so we see the effective mass and effective G factor. So the mass, the G factor get renormalized, you get new values for them. Then we use the envelope function approximation for the case in which you have, let's say, heterostructure, or the fields depends on position, and how to go from there to the spin orbit coupling in semiconductor heterostructure. And specifically, we'll be discussing the so-called Rajva spin orbit coupling. So let's see how we go from atoms to materials. So we have an atom, an individual atom. We know that we have different atomic levels, and according to the symmetry, we classify them as state, this state, and so on. To make an analogy with this, I can just consider a simpler example, which will be a quantum well. So you have a quantum well, I can have also these discrete energy levels inside the quantum well. Now, let's say that I have now 2 atoms instead of 1 atom. Okay. So let's say that they are far away from each other, so I have these 2 quantum wells, right? And these 2 quantum wells, because they are far away from each other, so they don't see each other, I still have these energy levels in the 2 quantum wells. Now, if I bring the 2 atoms close enough, so the states of these 2 quantum wells get coupled, and what happens is each of these levels split into 2 levels. Okay. And if I put 3 atoms, well, we have more splitting, and more and more and more. So the more atoms I put, the more they get splitted. So eventually, we end up with these bands, which is a lot of levels, but they are so close from each other that they are just form a quasi-continuum. Okay. So let's say for the 1s band, the 1s state, we'll get an S band, which a lot of states with energy very close from each other. So it's like a quasi-continuum here. Then we have a gap between 1s and 2s, and we have the second band, this 2s band, let's say, also with a lot of states and so on. So that's the way these electronic bands appear when you have materials. So it just comes from the levels of the atoms, which start to hybridize and form these quasi-continuums of the called electronic bands. The simplest model that maybe you have to take in some solid state course, you probably have seen this model, which is called the chronic spinning model. By the way, this chronic is the same that proposed this spin, right? So discussed it in the previous class. In this model, what you have is essentially 1D model. At the position of the atom, you have this big potential, this quantum well, if you like. And you go to make things easy to work easily with this. You take the limit in which these potentials are like delta functions, and you can calculate this analytically, and you get a transcendental equation just with tangent and cotangents and so on, sines, and you can solve it, and this is what you get here. So this is the dispersion relation. You see the solution here. You see 1 band here, then you have this gap, then you have the other band, then a gap, another band. So you start to get bands instead of discrete energy levels. So how these bands look like for real materials, well, depends very much on what is the structure of this material, how the atoms are arranged in it. So we'll be dealing in this lecture today with semiconductors. And so I have two examples of typical crystal structure for semiconductors. So this here, which is this diamond structure, and this is, for instance, for silicon or germanium. And so it is, all these atoms of silicons are in there. And of course, this is repeated periodically in the system. Okay. So in the system, one can find actually a point of inversion symmetry, which is this point here. So A and B, you can see actually like these two lattices, one inside the other. So you look at the atoms here, some of the atoms, will form this lattice A, and some of the other atoms will form this lattice B. And then they, when you extend them periodically, you will go on the other side, you will have this P prime and A prime. But all of them are equal, so because you have silicon atoms, so you can actually invert one into the other. So you have inversion symmetry in these materials. Now you have compounds, typically of these 2,6 or 3,5 semiconductor. You will have another structure which is called the zinc blende structure, which is essentially what is showing these schematics here. So here is one of these. We have the gallium. This is for the case of gallium arsenide, but all of these examples here have also the same structure, but of course with different atoms. So in your range, you look at the atoms, the arsenic atom in that case, you will have, they will form a structure like in this cube here, yellow one, and the gallium atoms will be forming a structure in this magenta or purple cube. And so you extend it periodically. What you see on the other side is just this B prime and A prime. Before, in that case, you can change A, when you do this inversion symmetry, A goes to A prime, B goes to B prime, but they are equal, so you get the same lattice. Now in this case, because in A you have arsenic, A and B are different, because in A you have arsenic atoms, and in B you have gallium atoms. So when you change A to A prime, you don't get the same lattice. So it means that there is no point of inversion symmetry in this case. So this structure really tells you that there's going to be a big difference between this, spin-orbit coupling effect in these materials and this other. So they have different symmetry, and in the case of the diamond structure, you have an inversion point of inversion symmetry in this structure. In the other case, you don't have it. Okay. So I won't discuss this today, the consequences of this lack of inversion symmetry in the bulk of the material, but we will see this in the next lecture. Okay. Now going back to the levels, so this is what the band structure of these zinc blende materials look like. So I will be focusing on the zinc blende structure. So these are the most, in which materials in which you can have a sizable spin-orbit coupling, so that I will be focusing on them, on this binary compound for 2,6 or 3,5 materials. And this is what happened actually. So essentially there are two kind of orbitals that are important here, the S and P, and they give rise to S bands and P bands. So this is the band structure of this zinc blende semiconductor. You have a conduction band, which is typically called gamma C, 6C. So the origin of this labeling is just from symmetry, so it's not relevant for what I'm going to talk. But anyway, so you have a conduction band here, then you have this valence band, so this is conduction electrons, and here you have the valence band. So you have two heavy hole, two bands. One is heavy hole, is HH, heavy hole. The other one is called the light hole band, and then you have a spin orbit split band, which is the green one. So there are of course more bands, but these are the most relevant for the case I'm going to talk today. these 8 bands. So we have 8 bands, because we have 4, but we have in each of these, we have a band for a spin up, a spin down. So I have 8 for it, right? 8 bands. So it means that the calculations are going to be long, because you have 8 bands, your basis will be of size 8, you will end up with a Hamiltonian that is 8 by 8. So we have to figure out how to transform this and to get something just for the conduction electron, so that will be 2 by 2. So what we do here, because
So we can make a short break because they are having typical thing to make a short break.
oh sure, yes.
Or if you want to finish something.
I will finish this slide and then.
Oh, okay.
So what is the idea of doing of what I'm going to do? So I don't know what is the we have we want to calculate the bands in this material, the electronic bands, and I don't know what is the potential of all these atoms are there. So I just know the symmetry that this material has. Okay. The idea is I will just use this symmetry to find a Hamiltonian which will depend on some parameters, and these parameters I will extract from the experiment. So that is the idea of this so-called K dot P approximation, which I will explain in a moment. So we are dealing with 2 kind of bands, P and S. So we have S states that I will denote with this S. So these are the atomic orbitals. So if we have an atom, but we now have a material, so we have bands. From the S atomic orbital, we have S bands. From the P orbital, we have Px, Py, and Pc, where we have then these X, Y, and Z bands. Okay. So we know the symmetry of the S and P orbitals, and they are related, for the case of the atoms, to these spherical harmonics. Okay. So I will then assume that my bands will have a function that I don't know what it is. I don't know exactly what are these 5, but they transform in the same way like the spherical harmonics. Okay, that is the idea. Then I can decompose these bands. So I will go from Cartesian coordinates to spherical coordinates. I can express these bands in terms of these spherical harmonics. Well, in the case of the bands, I can express it in terms of these terms here, which are going to be the eigenfunctions of the angular momentum, right? So the eigenfunctions of the spherical harmonics are the eigenfunctions of the angular momentum. So that's the idea. So I can transform this, my states X, Y, and Z, express it in terms of this spherical representation of this spherical harmonics, and vice versa. So also the spherical harmonics in terms. And when I say spherical harmonics, I mean it's not exactly a spherical harmonic. It's just something that transforms like a spherical harmonics. Okay. All right. So let's take a break.
Excellent, take a break. Because they need to go for a liquor.
Okay.